In this podcast, I'm going to give you a definition of a piecewise function and then several examples of the graphs of a piecewise function. So starting off, a piecewise function is something that you might learn like in an Algebra 2 class or above, and it's basically a function that's made up of pieces of other functions. And usually there's going to be some kind of restriction on the domain that tells you which piece of the function you want to use. Now, a classic example of a piecewise function is the absolute value function. I could define the function like this, and you would just be expected to know that anytime you put a value in there, you're going to get the positive version of it. But I could also define it in this piecewise manner where it's a little bit more detailed. It tells you if you have values that are less than 0, which are negative, that means negative, then you're going to take the opposite of a negative, which of course turns out to be a positive. If you have a positive value and you plug that in there, the positive will just equal the positive. There's no change to that value. And that's just another way to describe absolute value. If I were to graph this, you could consider the fact that the top piece, y equals negative x, is a line with a slope of -1 and a y-intercept of 0. But I'm only going to graph the left-hand side of this line because I only want values that are negative to follow that piece. If I then turn it around and say y equals positive x, that's going to follow the right-hand side. I have a line with a slope of 1 and a y-intercept of 0, and I end up with that classic V shape that I get for an absolute value function. All right, now let's go on to graphing some other types of piecewise functions. Again, this is an example that I might teach in an Algebra 2 class, college algebra. And here I've got two pieces of two linear function pieces, okay? And 0 is the place in the domain where we switch from one piece to the other. Okay, now the method that I like to teach my students is to make a table of values. And there are definitely shortcut ways to do this, but this is usually what I teach first. Okay, now, if I pick values for x, now looking at my graph in front of me, I've got values on the x-axis from -6 to 6. If I pick any values, let's say I pick -4, -2, -1, 0, 1, 3, and you can pick anything you want. At this point, right in between -1 and 0, I'm going to have to switch from one equation to the other. These values are all less than 0, and these values are all greater than or equal to 0. So I'm going to have to use this equation for the top 3 and then the bottom equation for the bottom 3. That's pretty easy. Okay, so if I plug -4 in the top here, -4 minus 1 is -5. If I do the same for -2, I get -3, and -1 minus 1 is -2. Then I switch over, I plug 0 in here. 0 plus 3 is 3, 1 plus 3 is 4, 3 plus 3 is 6. Now if I plot these points, -4 goes with -5, -2 and -3, -1, -2, and then 0 goes with 3, 1 goes with 4, and 3 goes with 6. Okay, now normally if I'm going to draw on a line, I put arrows on both ends, but I don't want to put arrows on both ends of these pieces. I want to put an arrow on the left-hand side of the bottom one and an arrow on the right-hand side of this top one. Now there's one little piece that's missing here, and that's what happens in between -1 and 0. It doesn't say here that we can only use integer values. So we could assume, for example, that we could use -1/2. And if I were to use -1/2, I'd have to put it in the top equation because -1/2 is less than 0. So what happens here, you guys, what I oftentimes recommend students is to actually put 0 into this equation to show what the line is going to go close to. 0 minus 1 is -1. So the line's going to keep going until I get close to 0, -1, but it's not going to equal 0, -1. So I put an open circle at 0, -1 to show that I'm getting close, but then I'm going to jump up to the other piece of the line once the domain hits 0. Okay, now, if you're graphing a piecewise function and you end up getting something like this, you get two pieces of a line that are one right on top of each other, then you know you made a mistake because that would not be a function that would fail the vertical line test. Okay, so it still needs to pass the vertical line test. Now, graphing a piecewise function in your graphing calculator isn't necessarily easy, but it is possible. And when I set this podcast up, I actually typed this one in, and I'll show you how I did it. If you go to y equals, type each piece of the function with parentheses around it, and then type another set of parentheses for the domain. It's almost like you're saying the function is being multiplied by part of the domain. And then to get the inequality symbol, go to second, and then go to test, which is right above the math button, and it gives you the choices in there for the inequality. Okay. Now, if I hit graph, I end up with exactly what we graphed. The only thing you can't really see here is the open and closed circle. Now, if I look at my table of values, it'll just show you zeros where it doesn't graph that part of the function. Okay. All right. Now, I have two more examples that are that have just a few other things added to them. In the second example, I have a piece of a line and then I have a piece of a parabola. And I had the changeover spot in the domain not be at the y-axis, but be at the line x equals 2. Okay, so again, if I make a table of values here, and I pick some values that are greater than or less than 2, let's say I pick -2, 0, 1, and then I am going to put 2 into this just to see. Oh yeah, 2 will be my darkened circle. All right, and then I'm also going to put 2 in the bottom one. This one's going to be an open circle though, because we can't actually equal 2 in the bottom one. And then I'll put in 3 and 4, and that's probably good. All right, so if I follow the linear function on the top, -2 minus 1 is -3, 0 minus 1 is -1, 1 minus 1 is 0, and 2 minus 1 is 1. And then if I put 2 into the bottom one, 2 squared is 4. The opposite of 4 is -4, plus 4 is 0. Make sure you square first, then take the opposite. If I plug 3 in there, 3 squared is 9. -9 plus 4 makes -5. Okay. Wait, did I do something wrong here? Nope, that's right. Okay, and then the last one, if I put 4 in there, 4 squared is 16. The opposite of 16 plus 4 is -12. Sorry about that. Okay, let's graph our points. -2 goes with -3. 0 goes with -1. 1 goes with 0. 2 goes with 1. I have the line, and I'm going to put the arrow on the left-hand side. Okay. Then I skip up, actually down, 2, 0, open circle. 3 goes with -5. And then 4 goes with -12, which is off my graph. Okay. Now, some people would say that a good way to do this is just to graph both parts of the function and not even think about the domain at first. So graph that linear function and graph that quadratic function. And if you think about graphing a quadratic function like y equals -x squared plus 4, you would have had a vertex at 4. And then because it's going down, I would have plotted, it would have looked like this. Okay, and then people say once you graph it, then go ahead and erase the part that you don't need. That's certainly a method that you can use. Okay, last one. This is going to be a piecewise function where we have 3 pieces. And 2 of the 3 pieces, the top and the bottom one, are horizontal pieces of horizontal lines. So if you think of the function y equals -3 and y equals 1, those are just horizontal lines. But the one in the middle, y equals x minus 3, is a diagonal line that has slope and y-intercept. All right, so rather than make a table of values here, I'm just going to reason through this one. For x values that are negative, I want my y value to equal -3. So for -5, I'm at -3, -3, I'm at -3, -2, I'm at -3, all the way up to 0, -3 with an open circle. Open circle because there's no line underneath that. All right, then between 0 and 4, I have a slanted line that has a y-intercept at -3 and then a slope of 1. Okay, and then from 4 on, so 4, 5, 6, 7, I'm going to have values of 1. Now in this case, because my closed circle at 0, -3 covered up my open circle, you don't have to have 2 circles there. I would actually, let me just fix that. There. The closed circle covers up the open circle, so it just looks closed. Okay. Now I didn't do an example of a step piecewise function, but a stepwise function would be all horizontal steps. So all the pieces would be horizontal lines. And there you have it. Thank you for listening.